All right, hello everyone. So we are going to get into chapter 10 now, which is actually our first bit of chemistry that we're talking about, meaning chemical reactions. Up until this point, we've been learning a lot of background information that we need in order to talk about chemical reactions. This is our first time that we're going to see chemical reactions, right? So first, just an introduction to chemical reactions. An essence of a chemical reactions is the making and breaking of covalent bonds. Okay. Um, so being able just to identify sort of processes, it's not a chemical reaction unless there's a rearrangement of atoms, unless there's a making and or breaking of chemical bonds. So for example, the rusting of this horseshoe here is an example of a chemical reaction because it starts off as iron, and then what happens in rusting is it's oxidized, what they call it, where there's oxygen added onto that iron. So you go from being just iron all by itself to now being iron oxide. This would be a chemical reaction because you're making these new iron oxygen bonds. Same thing when you're baking a cake. Actually, a lot of cooking, not all of cooking, but a lot of cooking involves chemical reactions. Baking most certainly does. It involves um, sort of the breaking down of proteins and linking other proteins together, blah, blah, blah. It's very complicated chemical reactions, actually. But nonetheless, you're making and breaking chemical bonds when you're cooking. So yeah, so cooking would be another example, or baking a cake and specifically would be an example of another chemical reaction, right? But again, all about rearrangement of atoms or making and breaking chemical bonds. You can't create or destroy atoms though. So in this case, so for iron, really it's iron plus oxygen, a gas all by itself, those mix together to form the iron oxide, right? So that's why rusting happens in the presence of oxygen. Yeah, so there's no such thing as making an atom from nothing. It's all about just rearranging the atoms and who's bonded to who. So then sort of just being able to recognize what would be a chemical reaction versus a non-chemical reaction. So over here, this is what we're going to start with. This is our starting material here. And you can see that each of these green beads is bound to a red bead, right? So these are all represent individual molecules where you have a green atom bound to a red atom. So which one of these, B, C, or D, represents a chemical change? Remember, it's all about the rearrangement of those atoms. So let's look at C in particular, we can see that the individual bonds between those two atoms, between my red and my green atom, have been broken. So this would constitute a chemical reaction, okay, or a chemical change. Because again, it's all about making or breaking chemical bonds. In this particular instance, these bonds were broken. So boom, that's a chemical reaction. If I look at B, now all of a sudden, all my red atoms are bound to other red atoms and all my green atoms are bound to other green atoms. So that means not only was the bond broken between my red and my green marbles, right? So I had to break these bonds here, and then I reformed new bonds. So this would also be a chemical reaction. If I look at D, I have this was probably a liquid phase right here, maybe a solid, but probably a liquid phase. And then over here in D, they're in the gas phase. But notably, there were no bonds broken and there were no new bonds made. So this would not be a chemical change. This would be a physical change, right? So going from ice to liquid water to steam, you still have H2O, right? You haven't done anything chemically to the water molecule. So those are examples of physical changes, not chemical changes. All right, and so like the holy grail of how we represent a chemical reaction is the chemical equation. Okay, so that's what this guy down here is, a chemical equation. It's a statement about what's reacting with what and what's being produced. Okay. It's sort of helpful to get in the habit of looking at these chemical reactions and reading them as if they were just sentences. So for example, this is ammonia. Ammonia actually isn't one that you would necessarily know. Ammonia reacts with hydrochloric acid or hydrochloride. Ammonia and hydrochloride react to produce ammonium chloride, right? So this side, this little arrow here means that there's a reaction going on between your two starting molecules. We call everything on the left-hand side of a chemical equation the reactants. So these would be reactants. And everything on the right-hand side of the chemical equation are the products of the reaction. So our reactants are ammonia and hydrochloric acid. Reactants are always consumed in a chemical reaction. So actually, let's color code. Reactants are consumed in a chemical reaction, and products are generated. Products are what are formed in a chemical reaction, right? So this chemical reaction is consuming ammonia and hydrochloric acid. These two are reacting with one another to form this new product, which would be ammonium chloride. Okay, so reactants are what's consumed in a chemical reaction, and products are what's formed in a chemical reaction. One sort of thing to note is, remember, we have these diatomic molecules, all right? And actually, I'm not going to have you guys worry so much about phosphorus, but all these other ones, these diatomic ones, we have to know. So remember, there's this little trick that I taught you. If you're looking at a periodic table, there are 7 diatomic molecules. They include the halogens all the way to nitrogen. So they form a 7 on the table. And then you just have to remember hydrogen as well. So those are the 7 diatomic molecules. They'll form a 7 on your periodic table. And what it means is that each of these elements, when they're found out in nature, they're found as diatomic molecules. So nitrogen, when you find that outside, so actually the air that you breathe is majority nitrogen. It's N2, 2 nitrogen atoms bound to one another. Same with oxygen. The oxygen that we breathe in is O2. Again, all those halogens are diatomic and hydrogen. Okay, so you want to be able to, just looking at the periodic table, you want to be able to spot what those diatomic elements are. The reason why I bring this up is because it can be confusing when we refer to these in chemical reactions. So for example, hydrogen and oxygen react to form water. I'm talking about diatomic hydrogen gas, H2 plus O2, that's oxygen, react to form H2O. You'll see I have this habit of always drawing these double-sided arrows. That is a symbol for an equilibrium reaction. It's kind of above our pay grade at this point, but if you draw the one-headed arrows, that's fine as well. It's kind of just a habit that I have. But anyway, so hydrogen and oxygen react to form water. What I really mean is diatomic hydrogen and diatomic oxygen react to form water. So you have to know what the diatomic elements are, and that when we refer to hydrogen in a reaction, we're really referring to hydrogen gas, because you really just don't find hydrogen all by itself in nature. It doesn't exist. It's always bound to something else. And if you're talking about pure hydrogen, it's always bound to itself. All right, so you got to keep that in mind. I try to get in the habit of saying hydrogen gas and oxygen gas to indicate that I'm talking about the molecular compound and not the element itself. But that's not really convention. You'll see it just like this. Hydrogen and oxygen react to form water, and you have to know it's talking about diatomic hydrogen and diatomic oxygen.